Hello viewers, I Neela welcome you to the second part of the chapter of probability. In this chapter, we'll study the rest of the topics of probability such as independent events, multiplication theorem, Bayes theorem, random variable, discrete probability distribution and mathematical expectations. So we'll first acquaint ourselves with the terms which are going to be used in the discussion. So let's understand the following concepts before proceeding further. Independent event. Two events are said to be independent if occurrence or non-occurrence of either of them does not affect the probability of the occurrence of the other. If the events are not independent, we say that they are dependent. For example, suppose two coins are tossed. If we let A denote the event tossing head with the first coin and B denotes the event tossing tail with the second coin, then A and B are called independent events. Similarly, if we draw a card from our deck of 52 playing cards and replace it before drawing the second card, then the result of the second draw is independent of the first draw. However, if the first card drawn is not replaced, then the second draw is dependent on the first draw. For example, if two events say A and B are independent, then the following events A bar and B bar and A and B bar and A bar and B are also independent. Let's see the multiplication theorem of probability. The following theorem, called the multiplication theorem, provides a technique for finding the probability of joint occurrence of two events A and B. Let's see the multiplication theorem. It says if A and B are two events of a sample space S, then probability of A intersection B is equal to probability of A times probability of B by A, where probability of A is greater than 0. Alternatively, probability of A intersection B is equal to probability of B times probability of A by B, where probability of B is again greater than 0. So we have a proof to this. To prove the theorem, assume that the sample space S has n possible equally likely outcomes. Suppose event B has m outcomes while A intersection B has k outcomes. So k is greater than equal to m. Then we have probability of B equals to number of outcomes favorable to B divided by n. So that is equal to m by n. And the probability of A intersection B is equal to number of outcomes favorable to A intersection B divided by n. So that is equal to k by n. We know we compute probability of A by B, the probability that event A occurs that B has already occurred. Since we assume B has occurred, our thinking may be restricted to set B as our new sample space. With respect to the new sample space B, the number of elements favorable to A consists of a count of those elements in A intersection B. So, probability of A given B is equal to number of outcomes favorable to A intersection B divided by number of outcomes favorable to B, which is equal to k by m. Divide numerator and the denominator by n. The total number of elements in the original sample space we obtain will be probability of A given B is equal to k by n divided by m by n. So that is equal to probability of A intersection B divided by probability of B, where probability of B is not equal to 0. Now multiplying both sides of the equation by probability of B. So we have probability of A intersection B equals to probability of A times probability of B given A. Similarly, probability of A intersection B is equal to probability of B times probability of A given B. So we have for this, if A and B are two events of a sample space S, then first thing, probability of A given B is equal to probability of A intersection B divided by probability of B, where probability of B is not equal to 0. Second, probability of B given A will be equal to probability of A intersection B divided by probability of A, where again probability of A is not equal to 0. Now let's see the next one, that is multiplication theorem for independent events. If two events A and B are independent, then the probability of A intersection B will be equal to probability of A times probability of B. That is, the probability of joint occurrence of two independent events is a product of their respective probabilities. We'll see an example for this. A box of 9 golf gloves contains 2 left-handed and 7 right-handed gloves. If 2 gloves are randomly selected from the box without replacement, what is the probability that, first thing, both gloves are right-handed, and second thing, one left-handed and one right-handed glove is there? The second bit says that if 2 gloves are randomly selected with a replacement, what is the probability that they would be right-handed? So we'll see solution to this. The box contains 9 golf clubs, 2 left-handed and 7 right-handed. So let's see solution to the first part first. Gloves drawn without replacement. The number of ways in which 2 gloves can be drawn out of 9 gloves is given as 9C2, which gives the exhaustive number of ways. Now the A part, the number of cases favorable to the event both gloves are right-handed is 7C2. Required probability will be equal to 7C2 divided by 9C2. So that is equal to 7 by 2. The B part, the number of cases favorable to the event, one left-handed and one right-handed glove. So this is equal to 2C1 times 7C1. So required probability will be 2C1 times 7C1 divided by 9C2. That will give us 7 by 18. Let's see the next bit, that is second one. If 2 gloves are selected with replacement, the 2 draws are independent. Probability of both are right-handed gloves will be equal to probability of right-handed glove in the first draw times the probability of red-handed glove in the second draw. So that gives us 7 by 9 times 7 by 9, which is equal to 49 by 81. We'll see another example also. A dice is thrown. If it shows even numbers, 2 balls will be drawn from the box A. Otherwise, 2 balls will be drawn from box B. Box A contains 4 blacks, 6 white and 2 blue balls, while box B contains 2 black, 4 white and 2 blue balls. In both the cases, balls are drawn with replacement. Find the probability that both balls drawn are white. So we'll see the solution. Let's make A1 as the event which says box A is selected. Let's make A2 as the event which says box B is selected. And let's have an event E which says that 2 white balls are drawn with replacement from a box. We are interested in finding probability of E. Clearly, probability of E is given as, can be found out by using the formula probability of E intersection A1 plus probability of E intersection A2. So that is equal to probability of A1 times probability of E given A1 plus probability of A2 times probability of E given A2. Now probability of A1 is equal to probability of throwing an even number, that is equal to 1 by 2. Probability of A2 is equal to probability of throwing an odd number, that is equal to again 1 by 2. So probability of E given A1 will be equal to 6 by 12 times 6 by 12, so that is equal to 1 by 4. And probability of E given A2 will be calculated as 4 by 8 times 4 by 8, so that is equal to again 1 by 4. Thus we can calculate probability of E, which is equal to 1 by 2 times 1 by 4 plus 1 by 2 times 1 by 4, which is equal to 1 by 4. Let's see another important theorem that is called Bayes theorem. In this section, we consider experiments with sample space that can be divided or partitioned into two or more mutually exclusive events. This study involves an application of the multiplication rule with the more involved calculation that leads us to the famous formula of Thomas Bayes, first published in 1763. In order to motivate Bayes theorem, let us consider the following situation involving two urns that are labeled 1 and 2. So, urn 1 contains 4 black and 3 white balls. Urn 2 contains 6 black and 5 white balls. Let A1 be the event that urn A1 is selected and A2 be the event that urn 2 is selected. Let E be the event that a black ball is drawn. So, two probabilities that can be calculated are: the first one, what is the probability of selecting urn A1 and then drawing a black ball, or find probability of A1 intersection E. Second, what is the probability of selecting urn 2 and then drawing a black ball, or find probability A2 intersection E. Assuming that each urn has an equal chance of being selected, we obtain the first thing, probability of A1 intersection E, which is equal to probability of A1 times probability of E given A1. This is equal to 1 by 2 times 4 by 7, which is equal to 2 by 7. And the second one, probability of A2 intersection E is equal to probability of A2 times probability of E given A2. So, that is equal to 1 by 2 times 6 by 11, which is equal to 3 by 11. Let us ask another question. If an urn is selected at random and a ball is drawn, what is the probability that the ball is a black ball? We could select a black ball in two ways. We could select urn 1 and then draw a black ball from the urn 1, or we could select urn 2 and then draw a black ball from the urn 2. Thus, we will have probability of E will be equal to probability of A1 intersection E plus probability of A2 intersection E. So, which is equal to probability of A1 times probability of E given A1 plus probability of A2 times probability of E given A2. Let us make this equation 1. So, this is equal to 2 by 7 times 3 by 11, that is equal to 22 plus 21 divide the whole thing divided by 77, which is giving us 43 by 77. We turn to a more complicated question now. Suppose in the above experiment, it is known that a black ball had been drawn. What is the probability that the black ball came from urn 1, or the probability of A1 given E? We observe that the drawing of a black ball could have occurred in two ways. Urn 1 has chosen and the black ball is drawn from urn 1, or urn 2 was chosen and the black ball is drawn from the urn 2. Only the first possibility involves urn 1 and hence is of interest. Furthermore, by using the multiplication theorem to find a conditional probability, it follows that probability of A1 given E is equal to probability of A1 intersection E divided by probability of E. But probability of A1 intersection E is equal to probability of A1 times probability of E given A1. And from equation 1, we have probability of E is equal to probability of A1 times probability of E given A1. So, that is equal to probability of A2 times probability of E given A2. Thus, probability of A1 given E is equal to probability of A1 times probability of E given A1. The whole thing is divided by probability of A1 times probability of E given A1 plus probability of A2 times probability of E given A2. So, that gives us 1 by 2 times 4 by 7, the whole thing divided by 1 by 2 times 4 by 7 plus 1 by 2 times 6 by 11. This is equal to 2 by 7, the whole thing divided by 43 by 77, which gives us 2 by 7 times 77 by 43, that is equal to 22 by 43. The above formula for finding probability of A1 given E is a special case of the theorem known as Bayes theorem. So, we can generalize Bayes theorem and we can write a formula for this. Let's take A1, A2 and AN be n mutually exclusive events such that they form a partition of the sample space S. That is, A1 union A2 union so on AN equals to the sample space S. Let E be an event so that E can occur in conjunction with only one of the events A1, A2 so on AN, and P probability of E not equal to 0. Then the conditional probability of occurrence of AI, where I is equal to 1, 2 or so on till n, given that if event E has occurred, is given by probability of AI by given that E has occurred equals to probability of AI times probability of E given AI divided by probability of A1 times probability of E given A1 plus probability of A2 times probability of E given A2 plus so on probability of n times probability of E given AN, where I is 1, 2 so on, like it go on to n. So we have a proof for this as well. We have AI intersection E divided by probability of AI given E, which is equal to probability of P. So that is, let's make this equation 1. Also we have probability of AI intersection E equals to probability of AI times probability of E by given AI. That's, let's make this equation number 2. Since A1, A2 and so on AN are mutually exclusive and S is equal to A1 union A2 union so on AN, E is equal to E intersection S and E intersection A1 union A2 union so on AN. So this is equal to E intersection A1 union E intersection A2 union so on E intersection AN. Clearly E intersection A1 and E intersection A2 so on E intersection AN are mutually exclusive events. Hence, by addition theorem of probability, we will have probability of E equals to probability of E intersection A1 plus probability of E intersection A2 plus so on probability of E intersection AN. So that is equal to probability of A1 times probability of E given A1 plus probability of A2 times probability of E given A2 plus so on probability of AN times probability of E given AN. So let's make this equation 3. Now substituting in equation 1 the expression of probability of E obtained in equation 3 and the expression of probability of AI intersection E obtained in equation number 2, we get probability of AI given E equals to probability of AI times probability of E given AI. The whole thing is divided again by probability of A1 times probability of E given A1 plus probability of A2 times probability of E given A2 plus so on probability of AN times probability of E given AN. So this completes the whole proof. Now we'll look at an example now. An urn contains 4 balls. 2 balls are drawn at random and are found to be white. What is the probability that at all the balls are white? We'll see the solution. Since 2 balls are drawn and they are found to be white, the urn must have at least 2 white balls. Let us define the following events. Event A1, which says that the urn contains 2 white balls. Event A2, that says the urn contains 3 white balls. Event A3, that says the urn contains 4 white balls. And we have an event E, which says that 2 white balls are drawn. The events A1, A2 and A3 are equally likely, and we are given the following probabilities as well. Probability of A1 is given as 1 by 3. Probability of E given A1 is given as 2C2 by 4C2, which is equal to 1 by 6. Probability of A2 is also given as 1 by 3. We know the probability of E given A2 will be 3C2 divided by 4C2, that is equal to 1 by 2. Probability of A3 is also given as 1 by 3, and we have calculated probability of E given A3 will be equal to 4C2 divided by 4C2, which is equal to 1. Now we wish to find probability of A3 given E. So using the base formula, we will have again probability of A3 given E will be equal to probability of A3 given E is equal to probability of A3 times probability of E given A3, the whole thing is divided by probability of A1 times probability of E given A1 plus probability of A2 times probability of E given A2 plus probability of A3 times probability of E given A3. This is equal to 1 by 3 times 1, the whole thing divided by 1 by 3 times 1 by 6 plus 1 by 3 times 1 by 2 plus 1 by 3 times 1, which is equal to 1 by 3 divided by 1 by 18 plus 1 by 6 plus 1 by 3, which is equal to 1 by 3 divided by 10 by 18. So that is equal to 3 by 5, which is giving us 0.6. Let's come to the next definition, that is random variable. When we perform a random experiment, we are often interested not in a particular outcome, but rather in some number associated with the outcome. For example, in tossing a coin 3 times, we may be interested in the number of heads occurred, regardless of a particular sequence in which the head appears. If we let x, capital X, be a variable that represents the number of heads that occur, then the only values that x can assume are 0, 1, 2 and 3. The real numbers assigned to each outcome of an experiment is called a random variable. The formal definition of a random variable involves the concept of a real valued function. Let's see the definition of random variable. A random variable is a function that assigns a real number to each outcome of an experiment. Thus, a random variable is a function from the sample space to an experiment into the set of real numbers. Usually, random variables are denoted by capital letters such as capital X, Y and capital Z, and the values that these variables assume may be denoted by corresponding lowercase letters like X, Y, Z again. For example, suppose a fair die is tossed. If we let x, capital X, be a variable that represents a number that shows on top, then capital X is a random variable and the values that x can assume will be 1, 2, 3, 4, 5 and 6. Second example, suppose a die is successively thrown until 6 turns up. Now in this case, if x is the number of such throws, then x is a random variable and assumes infinitely many values, like it can take 1, 2, 3 and so on. Third example, suppose a student takes an examination with a 2-hour time limit. If x, capital X, is again the number of minutes it takes to complete the examination, then x is a random variable again that can take on any value in the interval 0 to 120. So that brings us to the next topic, that is discrete and continuous random variables. So we have two types of random variable, discrete and continuous. These are the two types of random variables. Let's see the first one, a discrete random variable. It is a random variable that can assume only a finite number of values, can be placed in one-to-one correspondence with the positive integers. For example, random variable defined in the part A and part B are discrete. Second one, that is continuous random variable. It is a random variable that can assume any value in some interval. For example, random variable defined in the example C is a continuous one. Similarly, the heights and weights of the student in a class represents a continuous random variable. Now that brings us to the next topic, that is discrete probability distribution. A discrete random variable assumes each of its value with a certain probability. For example, in the case of tossing coin 3 times, the random variable capital X representing the number of heads assumes the value 2 with the probability 3 by 8. Since 3 of the 8 equally likely outcomes results in 2 heads and 1 tail. We can list all the possible values of x along with the associated probabilities in our table. That is called a discrete probability distribution and it is shown as this. So x takes the values 0, 1, 2, 3 and the corresponding probabilities to this x values will be 1 by 8, 3 by 8, 3 by 8, 1 by 8. So this table contains two rows. The first lists the values the random variable x can take on, and the second lists the corresponding probabilities. Let's see the definition for this. A table listing all possible values that a discrete random variable can take on along with the associated probabilities is called a discrete probability distribution. If capital X is a discrete random variable that can take on values x1, x2, so on xn with the corresponding probabilities p1, p2 and so on pn, then the probability distribution of x will be given as capital X. It will have values like x1, x2, so on xn. The corresponding probabilities to this will be p1, p2, so on pn. Frequently, it is convenient to respect all the probabilities of the random variable by a formula, which may also be termed as a probability distribution of the random variable. Such a formula would necessarily be a function defined on the range space of x. Thus, if x is a discrete random variable, then a function p, capital B, defined on the range space of x by probability of x equals to probability of capital X equals to small x. So, is the probability distribution of x. Note one thing over here, that is, since any two of the events x, capital X equals to x1, capital X equals to x2 and so on, capital X equals to xn, are mutually exclusive and the union of all these is a sample space, we note that the probability for any probability distribution, that is sigma I equals to I equals to 1 goes to n, will be equal to probability of 1 plus probability of 2 plus so on probability of n, and this whole thing will be equal to 1. Second thing to be noted here is, first point, probability of x lesser than equal to xi will be equal to probability of x, capital X equals to x1 plus probability of capital X equals to x2 plus so on probability of capital X equals to xi. So, this is equal to p1 plus p2 plus so on pi. Second one, probability of capital X greater than xi will be equal to 1 minus probability of x lesser than equal to xi. So, that is equal to 1 minus in bracket p1 plus p2 plus so on pi. Third note is, the probability distribution of a discrete random variable may be represented graphically as shown in the figure A. The vertical lines at each values of x are constructed so that their heights are equal to the corresponding probabilities. We will look at one of the example here. A random variable x, capital X, has the following probability distribution as given in the table. So, we are supposed to find first thing p, small p, and the second thing we are supposed to calculate e of x plus 2, that is expected value of x plus 2. So, we will see the solution for this. The first one, let us see the first part. Since sum of all the probabilities in a probability distribution is 1, we know. So, we have 1 by 6 plus p plus 1 by 4 plus p plus 1 by 6 equals to 1. Whole thing we are equating to 1. So, finally, we will get probability p equals to 5 by 24. Second part of the question, we have to calculate expected value of x plus 2. So, this is equal to expected value of x plus expected value of 2. So, that is equal to expected value of x plus 2. Now, let us calculate expected value of x. So, this is equal to minus 2 times 1 by 6 plus minus 1 times 5 by 24 plus 0 times 1 by 4 plus 1 times 5 by 24 plus 2 times 1 by 6. So, the whole thing is equal to 0. Thus, expected value of x plus 2 will be equal to 0 plus 2, which is equal to 2. Let us see the next one, that is mathematical expectation. If capital X is a discrete random variable which can assume value x1, x2, so on xn with the associated probabilities p1 equals to p probability of x when it is equal to x1 and probability of x when it is equal to x2 and so on, probability of n is equal to probability of x when it is equal to xn, then the expected value or the expectation of x denoted by mu or E, capital E of x, that is expected value of x, is defined as mu equals to expected value of x, which is equal to sigma I equals to 1 goes to n, that of xi times pi. So this is equal to x1 times p1 plus x2 times p2 plus so on xn times pn. The expected value of a random variable capital X is also called the mean of x. Thus, to calculate the expected value of a discrete random variable x, we multiply each value that the random variable can assume by the probability of occurrence of that value and then add these products. The expectation of a random variable x can be interpreted as the average value of x in the long run. For instance, if a coin is tossed 2 times and capital X denotes the number of heads, then x is a random variable which can assume value like 0, 1 and 2 with associated probabilities 1 by 4, 1 by 2 and 1 by 4. Thus, the mean of the random variable x will be given as expected value of x equals to 0 times 1 by 4 plus 1 times 1 by 2 plus 2 times 1 by 4, which is equal to 1. This means that if we toss the coin many times, the average number of heads per toss would be 1. Let's see some of the properties of expectations. First one, for any constant c, small c, expected value of c will be equal to c, that's same. That is, the expected value of a constant is a constant itself. Second thing, if capital X and Y are any two random variables, then expected value of x plus minus y will be equal to expected value of x plus minus expected value of y. That is, the expectation of the sum or the difference of two random variables is equal to the sum or difference of their expectations. Third thing, if c, small c is a constant and capital X is a random variable, then expected value of c times x will be equal to c times expected value of x. That is, the expectation of constant times a random variable is the constant times its expectation. So finally, we have learnt probability completely. In this script, we have discussed independent events and understood multiplication theorem and Bayes theorem. We have briefly explained the term random variables of probability. We have also learned discrete probability distribution and mathematical expectation with some good examples. So that gets us to the end of today's episode. We're ending here the chapter of probability, and we'll see you again discussing about our next topic on more wide variety. Till then, have a nice time. Thank you.
Thank you.